In this tutorial, one of the key things that we're going to explore is the concept of strong and weak acids and bases. And this will be a new concept, and what we're going to work to do both in this tutorial and through the in-class work is to differentiate between strong and weak and concentrated and dilute, and make sure that we can apply those terms appropriately for both acids and bases. We also want to find out, does a solution of a strong acid always have a low pH? And so again, some of the work that we will do here in the tutorial will set the background for that, and we'll continue to explore this in class. And then you need, I'll have a list of strong acids and bases that you need to know, that you need to be comfortable with and can recall. So we'll start by looking at a strong acid, and basically a strong acid is, the word strong is used to talk about the amount of dissociation that's taking place. And so we see here that a strong acid completely dissociates, and so the amount of dissociation is greater than 99%. And so if we take a look at that here in the diagram, we see that hydrochloric acid is an example of a strong acid. And we've got the chloride ion and then the hydronium ion, or again, you can picture this as H+. And what has happened is that, and we can see right here, that the HA, which is the sample sort of strong acid, has completely dissociated into H+ and A-. Another way of thinking about that is that there isn't any of this in the solution. And this equation right here is just taking the presence of water into account, and therefore then producing the hydronium ion. But again, this would be the key here that I want you to understand in the form that I will probably talk about the most, but both are relevant. So here we don't have any HA, we have complete dissociation. Because of that, we can say that the concentration of H+ is equal to the concentration of the original acid. So that if you had a 1 mole per liter solution of hydrochloric acid, then that would be equal to, so if that's your concentration of HCl, then that would be equal to both the concentration of Cl- and the concentration of H+ in your final solution, because that HCl would have completely dissociated. And here I have a list of strong acids that I want you to know. And so you'll see HCl, HBr, and HI, so they're all binary acids, and they're all halogen-based acids. Note that HF is not present here. HF is a weak acid. And then the other strong acids that I want you to know, so HNO3, H2SO4, and that's just the first dissociation, HClO3 and HClO4. So nitric acid, sulfuric acid, chloric acid, and perchloric acid are all strong acids, just like hydrochloric acid, hydrobromic acid, and hydroiodic acid. Now, when we talk about an acid being weak, I'm not necessarily talking about, I'm not talking about its pH. Rather, I'm talking about the degree of dissociation, or the amount of dissociation. What you see is that a weak acid actually only partially dissociates, so less than 50%, and quite often it's much, much less than 50%. And what that means is that you actually still have some of the molecules in their undissociated form, that they stay together. If we look at acetic acid as an example of a weak acid, we see in this picture here, we've got the acetic acid molecule, so the undissociated acid. We've got hydronium ions, which we know are produced in all acidic solutions, and then we have the acetate ion. And so that would be, like an example here would be HA, so that would be the acetic acid, and then you've got your protons which have been produced from the dissociation, and you've got the A-, so the acetate ion. But the big difference here is that you actually have some of these undissociated acid molecules in the solution. So because of that, you can't calculate the concentration of H+ directly from the concentration of the original acid. Or I should say that you can't calculate it based on the tools that we currently have in our toolbox, because we don't know the degree of dissociation. And one thing to mention here, that when you have a weak acid, I've got this reversible arrow, and what this says is that this reaction can go in the forward direction, where HA dissociates to H plus and A minus, or it can also go in the reverse direction, meaning that H plus and A minus can react together to form HA. And so those reversible arrows represent that the process shown here is reversible. It can go in both directions. The way we really want to focus on for now in grade 11 is that it means that the dissociation is not complete. And you might be wondering what the list of weak acids are. Well, basically, if an acid is not listed in this list up here of strong acids, then it's weak. And so there are a few exceptions to that. I didn't give you the absolute full list of strong acids. I gave you the list of strong acids that you need to know. But if you were given an acid and it's not in this list, then you consider it to be a weak acid. Now, with the acids, we can use either the Arrhenius theory or the Bronsted-Lowry theory to talk about the way that an acid behaves in solution. But for a strong base, we really do want to focus on treating them as Arrhenius bases. And what I mean by that is the definition of an Arrhenius base is a substance that dissociates to produce hydroxide ions in solution. And since all strong bases that we will work with are ionic hydroxides, we can say that this definition is true, that these bases will dissociate to produce OH minus, or the hydroxide ion in solution. And in fact, they're strong bases, so we can say that they will completely dissociate and produce OH minus in solution. And so just like a strong acid, we can calculate the concentration of OH minus from the original concentration of the strong base. So if I had a 1 molar solution of NaOH, then the concentration of OH minus ions in that solution would be 1 mole per liter. And we see that in the picture down below here, where the NaOH is added, and then it completely dissociates into Na plus and OH minus, and that's what's shown in the equation up above here, where we see that complete dissociation. There's no reversible arrow; it's a one-way arrow indicating that it is in fact complete. Some of the strong bases that you need to note again that they are all ionic hydroxides, and namely so you've got alkali metals and you've got alkaline earth metals, so the metals from group 1 and group 2 paired up with hydroxides. Those are all the strong bases that you need to know. So unlike strong bases, weak bases are treated as Bronsted-Lowry bases, meaning that we treat them as substances that are capable of accepting protons. So the difference here actually is best seen when we take a look at ammonia. If we just treated this as a Bronsted-Lowry base, as an Arrhenius base, the problem would be that the NH3 does not contain any OH minus, and so you wouldn't expect it to be a base because it wouldn't dissociate in water to yield OH minus ions. But you'll notice that when the NH3 is added to the water, that there are OH minus ions present. That's because the NH3 is accepting a proton. Where does the proton come from? Well, it actually comes from the water itself. And so we can see that in general terms right here, where the base, whatever it may be, is accepting a proton from water, and that proton, so removing a proton from this, removing an H and a positive charge from this, leads to the production of OH minus. And here we see the Hb plus has actually accepted, or the B, when it accepts the proton, forms the Hb plus. And so as in this example here, the B would be the NH3, the water is the water, the OH minus is the OH minus, and the Hb plus would be the NH4 plus. And so the NH3 and the NH4 plus are conjugate acid-base pairs because they differ only by a single proton. So in contrast to weak acids, we don't talk about weak bases not dissociating completely. Rather, we talk about them not reacting completely with water. They do not react 100% with water to form OH minus. And so what this means is that you're going to have some of the weak base, some of the NH3 in the solution. And yes, some OH minus will be produced, but you also have the unreacted NH3 in the solution as well. So another example of a weak base besides NH3 would be the CO3 2- or the carbonate ion, and that could be produced from the dissociation of Na2CO3. And this thing will completely dissociate. It's highly soluble, but then when this CO3 2- is interacting with the water in the solution, then it's only going to do so in it's only going to interact with it or react with it partially, right? Because again, you see this reversible arrow. And so this CO3 2- is acting as a base, which means it's accepting protons. And one of the reasons we learned that this thing might be a good candidate to accept protons is because it's negatively charged. And so this CO3 2- is a good acceptor of protons, and it accepts those protons from water to produce OH- and HCO3-, but it doesn't do so completely. And that's the same, or that is true for all weak bases. And so you might be asking, what are some other examples of weak bases? Well, just like we said for weak acids, if it's not strong, it's weak. And so you have the list of weak or strong bases given up above here. And so if it's not in this list and you're given it, then it will be a weak base. So the focus of this tutorial was really on this idea of strong and weak, and those terms both have to do with the amount or the degree of dissociation. And as mentioned before, the work that we do in class will help us dig a little bit deeper into how strong and weak are connected to, but also much different from the ideas of concentrated and dilute.